Hello everyone, welcome back to our YouTube channel of Developers and Coders Club. Myself Chetan and I am a student of NIT-A. Today we are here to solve a problem from recent contest of CodeChef and that is Starter 17. And the problem is X and Y tree which is fourth from the division 2. So before taking a deep dive in the problem, I will suggest to you all that please have patience for this problem because in it I am going to explain from scratch that how to implement entry and how to tackle these queries and all. So I don't know that what will be the length of this video, but that will be long. So yeah, let's start the problem. So the problem statement goes is that Chef has a tree consisting of n nodes, and the root node over this tree will be 1. Every node of this tree can be assigned a bind value that can be either 0 or that can be 1. Initially, every node is assigned 0. There are two terms. First one is AND value of the set, and the another one is good as. We define AND value of a set of nodes as the bitwise AND of all values of the nodes which are present in this set. And an edge in the tree is called good if after removing this edge the two trees which will often have the same AND value. So first see that what is these two lines are saying. First one is that AND value of a set. There will be a set like this, and I should say that will be a binary set because each element of this set can be either 1 or that can be 0. So AND value of this set can be either 1 or that can be 0. Just tell me that what will be the required condition for that the AND value of this set is 1. If all elements of this set are 1, then that is the only condition in which AND value of the set is 1. If a single 0 is present there, then AND value of this set will be 0. Because what is AND value? That is AND of this whole. Okay. So now we know that for making AND value of a set equal to 1, all elements of this set should be 1. And if a single 0 is present there, then the AND value of that set will be 0. So let me wipe it. Then we will see that what is the good edge. A good edge, an edge in the tree is called good if after removing this edge, the two trees which we will obtain have the same AND value. Just think that if I remove this edge, then there will be two trees. First one will be like this, and another one will be this. What is the AND value for this? For making AND value 0, a single 0 is enough, and here are 6 0, so this will be 0, and for this that will be 0. So AND value both are same, so this one will be a good edge. Okay, now let's see that what are the not good edges. If I want to find out any good not good edge in this tree, then if you think that you cannot find out any good edge, any not good edge. Why? Because in every set of tree, the bitwise AND value will be 0. Because for making bitwise AND value 1, I need all elements should be 1. But there is not a single element node which is having value 1. So all set will be having bitwise AND value 0 and that will be same. So if we talk for not bitwise, not good edge, then I have to replace some with 1. If I replace these two with 1, now let's see that what are not good edges. If I still talk for this, then this one will be the first set, first tree, and this one will be the another tree. Bitwise AND value for this will be 0, and for this there are 1, 2, 3, 4 zeros are here, and 1 0 is enough for that, but there are 4, so it will be 0. Bitwise AND value for this also 0. So that, yeah, that is good as well still. But if we talk for this edge, now let's see. One tree will be this, and another one will be this. Bitwise AND value for this tree is 0, but bitwise AND value for this tree is 1. Because there are only two nodes and both are having value 1. So that's our nodes. So this one will be a not a good edge. And same for this, same concept for this edge. There will be two trees. This one will be this, and another one will be this. Because the end value for this will be 0 and for this will be 1. So yeah, both are not same, so this will not be a good edge. So as of now, we know that what is the bitwise end of a set and what is a good edge and what are not. Okay. So yeah, that's enough. Now let's move further. We have to process Q queries. Each query is one of the following types. So each query will start with an integer. Either that can be 1 or that can be 2. If that is 1, then that will contain an extra information of u. See here. If that is 1, then there will be another integer which is having the information of node. And if that is 2, then there will not be anything after that 2. So let's just see that here. There are two queries. First one is that if that is 1 u, then if node u is a leaf node, initially all nodes are having value 0. Okay, now tell me that what is count of good edges in this tree? Count of good edges. Can you find out any edge which is not good in this? We cannot find out because every node is 0. So every subtree will have bitwise end value 0. So every edge of this tree will be a good edge and that is n minus 1. N is number of nodes. That is 1, 2, 3, 4, 5, 6, 7, 8. So 7 edges are there. Okay. But if I talk for general, then that will be n minus 1. So now, our first query is saying that if node u is a leaf node, then we will change its value to 1. Just like that, if node u is pointing out these type of nodes, then we will change its value to 1. Okay. Now, if that is not a leaf node, then what we will do? Change its value to AND value of all nodes in the subtree of u except u. So now what is the subtree of u? If we talk for that what is subtree of this node, then that will be, but before that I am imagining that this one is root node for this tree. For this whole tree, this is a root node. Now subtree for this root, subtree for this node will be this tree. Subtree for this node will be this one. This is for this. And subtree for this, that is root node, that will be the whole tree. So now we know that what is subtree. Okay. So that is saying that if that is not a leaf, then we will change its value to AND value of all nodes which are present in the subtree but except u. So if u is pointing to this node, then we will check that what is the value of AND value of the nodes which are present in the subtree of this, but we will not contain the self node. So this will be the part that is subtree of this node but except their node. What is the bitwise end value of this node? Then we will replace the value of this node with change its value to AND value of all nodes in the subtree of u except u. If that is 1, then we will change its value to 1, and if that is 0, then obviously that is already 0, so we will not change that. So now we know that what is first query is doing here, and in second query we are going to simply print that find the total number of good edges in that tree. In that position, means in that state where maybe because of first query some nodes are 1. In that state, what is the count of good edges there? If second query is asked there, then we will print the count of good ages. Okay. So now we know that what is the second query and first query is asking. So now we will proceed for solution. We know that we are going to print count of good ages. So initially, there what are the count of good ages are there? We know that is n minus 1. So I am making a variable like cur, and this one will have information about what is count of good ages in that person. That initially that is n minus 1. So now just think that our first query is asked there when u. We will check that u is leaf node or not. If that is a leaf node, don't think that how we will check that is that is leaf node or not. Just think that anyhow we will check. And if that is a leaf node, then what we will do? I have a map. I have a map, and name of this map is MPP. And this one is having information like if MPP of X, if this is 0, that is pointing that node will means value of node X is currently 0, and if that is 1, that means the value of node X is currently 1. So value for all nodes, MPP value of, for all nodes is initially 0. But if that is leaf node, then what we will do? We will change MPP for U with 1. That means we are saying that the current value of that node is has changed in 1. Okay. What changes it making on or this current variable that is pointing out our count of good ages in this person. Just think that if that is leaf node, this one is leaf node. I have changed it with 1. Now what is the count of good ages is there? All other are zeros are yet. Okay. Now what is count of good ages? Initially, all ages are good ages. But now this is 1. If we talk for this age, then this one will be have bitwise giant value 0, and this one will also have bitwise giant value 0 because of this 0. But if we talk for this age, then this one will have value 0 and this one will have value 1 because a single element is there and that is having value 1. So bitwise giant value will also be 1 and this is 0, that is not same. That means the count of good edges has decreased by 1. Yeah. So here what I will do, I will replace cur with cur minus 1. This is when the u is a leaf node. What if u is not a leaf node? For that I need some space. So I think I should replace, I should put it a little bit lower. Yeah, there it is okay. Now if u is not a leaf node, now again don't think that how we will check that that is leaf node or not. If that is a leaf not a leaf node, then what we will do? First we have to check that the subtree except u. Bitwise end value of the subtree except that node. Just think that u is pointing to this node. That is not a leaf node. For that we will check that the subtree except that node. What is bitwise end value for that? That means what is bitwise end value for this? Now how we will check that? Okay. I am just writing a line here. Just tell me that what is this is correct or not. Okay. if we want to mark any node with 1, then every child of this node should be 1. Now just tell me that is this condition enough if we want to, what is this, if we want to, okay, if we want to mark any node with 1, just think about this. If we want to mark this node with 1 because of first query, then every child of this node, what are the child of this node? First one is this, second one is this, and third one is this. There are three child of this node. Every child of this node should be 1. Now just tell me that is this one condition is enough for that, and is this condition is required for that? Okay. So what are we asking? The bitwise AND value for these 5 nodes should be 1. So these 3 should be 1. Yeah. Okay. That is correct. These should be 1. But there can be a point that what if these 3 are ones? Means these 3 are 1. In this time, this will be true. But these are 0. So now you will be like that these 3 are 1. So we can mark that with 1. But bitwise AND value of this is 0. So how is that possible? But before that, just tell me that if this is 1, so when I will, that means I have marked it with 1. When I have marked it 1, then also I check this condition. For this, I check that if I am going to mark it with 1, then every child of this node should be 1. But this is 0. That means if this is 0, then I will not mark it with 1. If this is 1, then obviously that will be also 1. And if this is 1, then obviously that will also be 1. That means if I am going to check for child of this node, then every child of these node will be 1. That will be automatically 1. I will not check for that. I am going to check only for child of that particular node. If those are 1, that means every node of that subtree will be 1. And bitwise AND value for that will be 1. So for means in conclusion, I want to check that is the bitwise AND value of the subtree except that node is 1 or not. If that is 1, then I am going to check, going to do some operation here. But for checking that, I am going to check only this one condition, that if you want to mark any node with 1, then every child of this node should be 1. Okay. Now just think that anyhow, I have checked this condition also. Okay. If I have checked this condition, then what we will do? What what if I change this with 1? Then what changes it is going to do with curve? Now this, let me wipe it, this O. That means that in that condition, this is 1, this is also 1, this is also 1, this is 1, this is 1, and this is 1. When I marked it 1, then I decrease count it 1. Why? Because this edge is going to not good. When I mark this one, then this is going to be not good. So when I mark this one, then what happened? Then this is going to be not good. Okay. And then I mark this one, then this is not. Then I mark this one, then this is not. And same when I mark this one, then this node is going to be not a good edge. Because when this was 0, mean when this node is 0, then this was good. Why? Because this side all are 0, this side a single 0 is present or is still there. Then its bitwise value will be 0. But when I mark it with 1, then bitwise AND value for this subtree is going to be 1, and that's making this edge as not a good edge. That means in both condition, either that is leaf node or that is a parent node, the count cur value will be decreased with 1. So here also I am going to replace cur with cur minus 1, and MPP of that u is going to be 1. Okay. And if second query is asked, then we will simply print. In case of 2, we will simply print CUR. Now there are some points that how we are going to check that is leaf node or not, and how we are going to check this possibility. Still we have done only 50% of solution. Why? Because these two lines of code is going to be 50% another code. Let me show it that. See here, this is our first condition and this is for second. But for checking these two conditions, I am going to write these full code. So still more than 50% code is enough here. So we are going to understand that one. So for that, I have these three things. First one is vector of int, and I am calling that with adjacency. Second one is parent, and third one is child one. And I have given these names to that. By the way, this child one is not a vector, that is a map of int, and name of this map is child one. Now, what are functionalities of these? For that, I'm going to simply let me write something. You will understand with that what are the okay. Picture. Okay. Now, what is adjacency is doing? Adjacency of one. What is this? This is a vector because this is vector of vector. So adjacency of one is containing all nodes. This is a vector, and that is having 10, 11, and 5. Adjacency of 10 for this tree, adjacency of 10 is having 3 and 7. Now how I am going to form this vector and vector, I will see that in next part. But now see this one, that what is this adjacency is containing. Okay, adjacency of if I see for 7, then that will be 9 and 2. That means for if I talk for any like adjacency for any u, then this will contain what are the child node for u. What are the child nodes of u? Adjacency of u, this is a vector and this will contain what are the child nodes of u. Then if I want to check that what are the count of childs of node u, then can I say that adjacency of u dot size, this is the count of child for node u. Is this true? Adjacency of u is going to be containing that what are the child of 1, that are 10, 11, and 5. What are child of 10, that is 3 and 7. And if I talk for adjacency of 4, because there are no child for that, then that will be a empty vector. and their size also will be 0. So if I want to find that what are the count of child for node u, then that will be adjacency of u dot size. Okay. Now one is parent. If I call for what is parent of like 11, then that will give me 1. Now how I am going to form this parent array, I will discuss it in later part. But now let's see that parent of 11 will contain 1. That means parent of u will contain what is the parent of node u. Like if we talk for parent of 7, that will contain, if we talk for 7, then that will contain 10. If for 8, that will contain 11. So now we know that what is parent vector, what is adjacency vector vector. Now what is this map of child 1? Now if I am going to mark with any, like if I mark 8 with 1, initially this was 0 and I have marked it with 1. Then what I am going to do? I will give information to 11 that one of your child have become 1. Like if I talk for 10, then when I mark 3 as 1, then I will give information to 10 that one of your child have become 1. So for that, this child 1 map is used because this is a map. So initial value will be 0. That is pointing that if I talk for 10, initially that will be 0. That means this is pointing out that count of number of child. What I am saying? Count of number of childs of u which are having value 1 वो इक्वल होंगे child 1 of u. This is functionality of child 1 map. And what is for parent? Parent of node u, that will be parent of u. And what to use for adjacency u? That is count of total child of node u, that will be adjacency of u dot size. I also can use map here, but yeah, whatever I use. These three things I am going to use here. If I am going to, yeah, for leaf node, I can simply check that if count of total child of node u that is 0, then that will be a leaf node. For checking leaf node, I am simply going to check this one, that if adjacency of u dot size is 0, then that will be a leaf node. And here, a third change is I also will do that I mentioned here, that if I am marking any node with 1, then I will give a information to its parent that one of your child have become 1. For that what I am going to do? I will check what is parent of this node u. What is parent of node u? Then let's see the child 1 of, for here, see here, if I am marking u with 1, then I will see that what is parent of u, and how I am going to find that? By this parent of node u, that is parent of parent u. Then I will mark child 1 of parent of u, where parent of u. I will see that I will say to a set increase it with 1, means one of child of no parent of node u, parent of node u, one of child of parent of node u have become 1. So here I am going to do this, and same here. I'm going to decrease curve with minus 1, amplitude of u with 1, and same thing here. Since if I write that here, then that will be child 1 of parent of u, increase it with 1, means parent of node u, child of parent of node u have become 1. One of child of parent of one of child of a parent of u have become 1. Okay, I'm going to confuse also. Same condition here and same condition on both sides. So now just tell me what I'm going to check here. I'm going to check here that adjacency of u dot size is 0 or not. If that is 0, then first change I'm going to do, that is MPP of u will be 1. Another one is curve will be decreased with 1. And another one will be child 1 or parent of u increase it with plus plus. And in another condition, if that is a not a leaf node, then I will check. What I am going to check there? I said here, if we want to mark any node with 1, then every child of this node should be 1. I have two information. One is count of number of child of u, which are having value 1. And another one is count of total child of node u. And what is this line is saying? If you want to mark any node with 1, then every child of this node should be 1. Then in total we want to say that these two values should be same. That means that all child should have value 1. That count of number of childs of u which are having value 1 should equal to count of total child. So for this I am going to check this condition, that if these both are same, then I am going to apply these operation. And operation in both condition are same. MPP of u should update with 1, should update with 1. Curve will be decreased by will, will be decreased by 1. And this condition is same in both condition. So operation are same in both condition. Let me write that here. That is first one is MPP of u, update that with 1. Another one is decrease curve with 1. And last one is child 1 value of parent of u increase with 1. Okay. These are three options which are going to be done with in both condition. And in first condition, what I am going to check, this is an issue that is going to be in white color, but I want that in black color. For checking leaf node, if we want for checking leaf node, I am going to check that adjacency of u dot size. If that is 0, that means that is a leaf node. And for checking second condition, what I am going to check for these both, adjacency of u dot size should equal to child 1 of u, should equal to child 1 of u. That means that total count of child of u should equal to total count of those child which are having value 1. Now one another point is these both conditions are not same, means if I talk for leaf node, then child of count of 1, what will be the count of total child of leaf node that are having value 1. If there are not any child of leaf node, then that will be obviously that this also for leaf node will be 0. So in total, I am going to say that I can check only one condition for these both. For leaf node, child 1 of this u will be 0. So why I am going to check these both conditions? How we can check? I can remove this one and can simply check this. If this is condition is satisfied, then we are going to do both operation same in both condition. So in total, I can apply these one condition only this condition one condition for first query and apply these three operation. Okay, now let's see the code part for only this for this. First I am going to take that how many queries are there, then I will check that that is one or two. If that is one, then I am going to find what is the value of node. If that is zero, means if that is already one, then I am going to not going to change anything. If that is zero, then I will check that okay one thing that what is I'm saying that here child one that is prnt here, means I have replaced that with prnt. Both things are same, just name is different. Child one of u should equal to adjacency of u dot size. If that is equal, then I am going to decrease curve with 1 and pp of u with 1 and PRNT. Here I am saying that child one of PRNT of u should increase with 1, then PRNT of parent of u should increase with 1. And okay, so this part I have discussed. Now this part, what is this? What we are going to do? Okay, this have let me redraw another tree. This way here I have draw another tree. Initially all values are 0. So value of curve initially that is 1, 2, 3, 4, 5, 6, 7, 8, 3, 3, 3, yeah, that is it. Just think that first of all I have updated this with 1. Then this is going to be not a good end. Then value of curve has become 7. Then if I ask query for this one, then that will not be changes. Means we have to change first leaf node. Then just think that I have done this and this one, then this is 6. Then for this is 5. Then for this is 4. Then setting for this, that is going to be not a good edge, this will be 3. Then for this will be 2. Then for this will be 1. And then for this one become to be 0. Means what is condition now? All nodes are 1. All nodes have become 1 except root node. And this is 0 still. Then can you figure out any node which is a good else? Can you figure out any edge which is good as? Because this is a only single 0. If you choose any edge, then only in one part this will be. So for at a part this will make that 0 and in another part that will be 1. So there cannot be any condition in which we can find out any like 0 0 or 1 1. So for this condition that is become 0. But now if I u is pointing to this, then this will be marked there and the value of current will be decreased with 1 and then that is going to be minus 1. So that is what is this now? If this have become 1, so what is the count of good edges now? All elements have become 1. All nodes having value 1 now. So all, can you figure out that all edges are going to be good edges now? Because every element is 1. So parts, if we make two part of for corresponding to any age, then for every part that bitwise end value will be one. So for every age that will be same and every age will be good age. Means when value of current is become minus one, then count of good edges will be n minus one. So this is a condition for that. So in second condition, I am going to check that if value of current become minus one, if that is minus one, then we will print n minus one, and if that is not minus one, then we will print curve. So that's all about query part. All actually we have solved all question, but we have not seen that how we are going to find out these parent node and these adjacency list. So now almost half code is here. Half code is still remaining. So now a BFS technique I have used here. So yeah, this video is going to be too much long. Now we have seen that till now we have discussed all question with this type of tree format, but we know that our question will not give over to this type of tree. That will give to us that total count of nodes are this that is 11 here, and these are edges which are connected here, and there will not be any sequence for that. That will be random. Like here I put 2 and 4 first, then 5 and 6 from here, then from 8 and 11. That can be either 8 or 11. That can be 11 or 8. It doesn't matter. And 9 and 7, 27 and 8. There will be total 10 edges there. Using a tree, if there are n nodes, then there will be n minus 1 edges. Okay. So
Okay, so I am going to explain that part with my code. So first of all, I will have a vector like this, vector tree. Then after taking the count of nodes, I will make a loop from I brought 0 to n minus 1. That means a loop is going n minus 1 times iterating, and in that I am going to take input like this, u and v, and then I will call a function which is add edge, and that will add a edge in tree from u to v. What is that? This is this add edge. That is tree a dot pushback b and b dot pushback a. That means if I talk for this, then tree of 7 will contain 2, 9 and 10 also, and tree of 2 will contain 4 and 7. Means all edges which are connected to this node, that is having the memory tree. Okay, after that I have a vector bool vector that is visited and a vector ends. Now I am going to call a BFS function that is rate, and that is a BFS function in which I am going to implement a queue, that is queue of pair. So first element is pointing to what, this is the current node and this is the parent node of that. First of all, I am going to push BFS is a queue. First of all, I am going to push initially I call for 1, so value of node is 1. So first of all, just think that this is our queue, BFS queue. Now first of all I will insert 1 and 1, then BFS, this is first element of BFS. Then I will iterate a loop that while BFS empit is not true, then access the first element of the BFS, then pop out this, then I will say that n's value of p dot first, that is currently 1. I will say that your parent is 1. As we know that 1 is our root node, so that parent will be that cell. So I am saying that your parent is 1. Then that means that now our value of n's 1 is 1. Then I will iterate for child of 1. That means tree of 1, and tree of 1, what is containing tree of 1? That is containing 10, 11 and 5. That means this loop will go for 10, value of child will become once 10, then 11, then 5. When it become 10, then it will check that is visited 10 is visited or not. If that is not visited, then I will push in BFS child and p dot first. That means what is child? That is 10. What is p dot first? That is currently 1. That means what is this? This will pointing out to parent of this node. In our queue, this will be inserted now. Then for 11, this will be inserted. Then for 5, this will be. This have deleted from here ps.pop, bfs.pop. Then again loop will be iterated, and again first element, that is 10 and 1, this will be accessed. Then I will say that ans.p.first, that is ans of 10, ans of 10, this is now 1. That means parent of 10, this is 1. And now I will iterate this for loop for tree of 10, that means all child of 10, that's are 3 and 7. And in our BFS queue, we will insert 3 and 10 and 7 and 10. That means in total what our ans vector is going to be stored. If I say that ans of u is equal to y, then that means that the parent of u is y. Parent of u is y. Parent of 10 is 1, parent of 1 is already 1. Here parent of 3 will be 10, 7 will be 10. So what is ans is going to be stored? If ans of u is y, then parent of u will be y. This is functionality of ans. Now after for this all function, again come here, I am going to make a parent array. Then I will say that for every I equal to 1 to n minus 1, for every I from 1 to n minus 1, I will see that adjacency of n's of I minus 1. N's of I minus 1, what is pointing out to n's of I minus 1? Just think that its value is, this is equal to u. That is pointing that parent of I plus 1, that is equal to u. So I am saying that adjacency of u, this is a vector, and insert I plus 1 in this. Parent of I plus 1 is u. That means adjacency of u is going to be store all childs of u, and that's what I said here. Where is that? Yeah, adjacency of u will contain total child of node u. So we have done with adjacency. Now our last target is for parent. Here I am saying that, what I am saying, parent of I plus 1 is u, and that thing I put here, parent of I plus 1 is going to be u. So yeah, I think that I have all discussed all part. I don't know that you are till here or not, but I started video on 5, maybe on 5 o'clock, and this is almost 7 o'clock. I spent 2 hours. No way. I think that, I hope that you understand the problem. See you in the next problem. Till then, happy coding.